Hello, and welcome to Week 1, Lecture 2 of CO 442-642 Graph Theory. Today we'll be talking about writing guidelines, the process of mathematical writing. So for mathematical writing, I ask the question, what are the most desirable outcomes for a proof? What are we looking for in the proof? Well, number one would be correctness. Why? Well, of course, we want math to be correct. The main concern of mathematics is logical proofs, and so we would like those to be correct. But is there anything else? What else would we be looking for? So maybe pause for a moment and think, what else would we want? Well, we also would like clarity. Or precision, depends on how you call it. But why would we want this? Why is it important that mathematical proofs not just be correct, but also clear or precise? Think for a moment as to why we would want this. Alright, so now I'll tell you. Well, in order to determine if a proof is correct, the proof needs to be clear and precise, both in what it is trying to prove and how it is trying to prove it. Right? If you want to know whether a proof is correct, you need to know what it's trying to prove. You need to know the statement of the claims, the lemmas, the theorems, and to be able to follow all of the individual steps in order to even verify whether that proof is correct. Indeed, it's helpful if you think of proofs as a recipe, logical steps to prove a theorem. Right? A theorem is a dish and we're trying to recreate it. And the proof is the recipe for that. Here are these logical steps, these inputs to create this dish. And in order to follow the recipe, the steps have to be clear, right? If you can't follow each step of the recipe, if you don't know what the step is saying, then how can you possibly make the dish? Okay, beyond that, I'd like to say that there's a third thing that would be desirable, a third outcome that goes beyond clarity and precision. And what is that? Well, I like to say it's ease of reading. And why is this? What does it mean? How is ease of reading different than just clarity or precision? Well, I'd like to say that beyond clarity, which is just, is it clear what's going on? Is the step clear? Is the proof clear? Is it the step precise? Can you follow that? That there's something more than that, if you think of the recipe analogy. It's more along the lines of being organized, or that you've written it with a natural progression, right? Have you broken down this recipe, this proof, into smaller components? Maybe group a couple steps here and a couple steps there, so that it's easier to follow. That you write it in a natural progression. If you're trying to bake a chicken, you don't say, pull chicken out of the oven and then back up. Oh, first you should have put it in the oven. Or first you should actually preheat the oven. Right? You do it in a logical, natural progression. Even if the recipe would be correct and or clear, without being that natural progression, it's helpful to the reader to do it in the order that they expect. To say it with the words they expect. And why is this? Well, maybe it's best to think of a proof as a transaction between you, the author of the proof, and your audience, which is this reader, this mythical imaginary reader. And the smoother that transaction is, it's the better for all involved. The reader may just even be you down the line, or yourself editing your own proof. You should be able to follow, and it's easier to do that editing, to know what you meant if you've organized, created a natural progression, made it easier on yourself. And what reader would not want that? If you want to read mathematical books or proofs or papers, of course you'd appreciate ease of reading as well. So maybe now let me go through some of the aspects of writing and how can you make your own writing better. So first I'd like to talk about organization. So proofs and research papers generally tend to be easier to read if they're organized with a top-down structure and or a logical progression. Maybe it's more sequential, just going in order, or maybe if you break it into smaller components, each of those follows a logical progression. So how do we go about doing this? Well, for research papers, we break into sections and subsections. We break up the overall proofs into smaller theorems and lemmas that can be useful to the overall picture. And we tease out often used concepts and give them new names or notation, so they'll be easier to remember. On a more granular level, for individual proofs, we break into claims, or if necessary, lemmas, which are then moved outside the proof of the theorem. And we define any often used, conceptually important terms and parameters for individual proofs, and we do that again outside of the proof. The proofs should just contain the ingredients, the simple steps of logic, that any definition of those ingredients should be moved outside, important lemmas outside. Claims can remain because they only work on their own in the context of the proof. They don't work on their own. As for proofs, there's even more that you can understand for organization. I would contend that you should begin proofs and/or claims with an indication of the type of proof, by induction, if it's by induction, or direct proof. Suppose not, for contradiction. That you should end proofs of theorems and claims with a QED or a box symbol. Again, organizational tips here. That you break out complicated equation into own lines and break up long equations into multiple lines. This is just easing the reader's ability to comprehend these very difficult equations. I would contend that proofs should have a natural structure to the rhythm of the proof. So if we're kind of doing cases, you say, first suppose that, do that case, and then say, now we assume that the other thing happens, and so on. And while we're talking about cases, I'd like to just mention one preference of personal style here, is that I generally prefer to avoid using explicitly defined cases where possible. So for example, doing a case 1, case 2, case 3, etc. And I'd just like to ask you why. Why would I prefer not to use cases? It seems so mathematical and logical and algorithmic, like writing code. Why would I maybe try to avoid that? So maybe pause for a moment and think about that. Okay, so here's my answer. Well, two main reasons. A big reason is it's unclear if all the cases are covered. If this is a contract, a transaction between you and the reader, you're putting a lot of trust that the reader is going to believe that you've done all the cases. And so if you haven't proven that these are all the cases, in some ways you're breaking that trust. Another reason is, where does it end? Right? If you're going to break into cases, you're going to break into case 1 and case 2. Well, then what if case 1 has subcases? Right? This naturally leads to subcasing. So then we'll do case 1, right? 1.1 and 1.2 and so on. But then subcases beget more subcases, and soon you have case 1.3.4.2. And this is unbearable. And imagine tracking that you've done all the various cases and subcases and all throughout without having proven that. So I think it's easier if instead you just create a natural logical flow and say, suppose that, now we suppose this instead, and now we finally may assume. The assume tells you, okay, we're really done. I can go back, I can check, yeah, this is where we're at now. Kind of more if-elsing from a coding standpoint instead of just breaking into all these cases. So that's all I wanted to say about the organizational aspect. So again, right now I'm trying to collect various writing tips, mostly for your assignments and or general well-being as a mathematical researcher. And a lot of these fall under organization, beginning and end, breaking out equations, avoiding cases, but still creating rhythm so as to create a better organization and ease for the reader. So those are the things you should be doing. Let me now talk instead about what you should avoid. So in writing proofs, what is essential to avoid when writing proofs? Now, if we go back to the desirable outcomes we said, you should probably have guessed the obvious one, which is falseness, incorrectness, writing wrong proofs. But is there another one? So stop and think a moment. Is there something maybe even more important than avoiding incorrectness? Well, here's my answer. It's avoiding imprecision. So we said that preciseness and clarity are important, and I would argue that we want to avoid imprecision comes first even before incorrectness. And why? Because in order to tell whether something's even correct, it needs to be precise. It's hard to spot the errors in proofs if the language is too vague. And so it's helpful to ourselves to become better writers, to learn how to avoid imprecision in order to actually detect our own mistakes. So maybe let me go over how best to avoid imprecision. How do we do this? Well, number one, label all relevant objects. So you want to give them names. So, for example, you're kind of introducing them as if into evidence, right? That let P, V1 up to Vk be a longest path in G. So each time you want to introduce an object, you give it a name, and then you kind of are entering it. Let this, let that. Now here, if we didn't need the vertices to be labeled V1 up to Vk, we could just say let P be, longest path in G prime. But if we want that additional flexibility with the labels and the vertices, then we do the V1 up to Vk, and so on. But labeling, that's very important. Once you've labeled everything, it's much easier to do operations on them, to make statements about your objects. So label. Number one, label. What else? Well, define. Define any new terms that you are using. So if you want to end up adding new terms in your notation, it's helpful if you don't just spring it on the reader, you tease it out, you put it before you make sure to define them. Or it can even just be helpful if you feel like you're using a concept many times, maybe just giving it a name, even if it's a poor name like good and bad, can be helpful to the reader. Ideally, it'd be something more brokerable, but defining terms can help to avoid imprecision, right? That's what we do in math. Make definitions so we all agree on what the terms mean. To that end, also avoiding informal language, contractions, hand-wavy statements. It's good to keep a professional tone. Number 4, and this might be more controversial, is to avoid proof by picture. So why is that? Why would I avoid proof? Everyone loves visuals and pictures, and they're so helpful. What do I mean? Why avoid proof by picture? Well, pictures could be helpful to the reader, I grant you that, if they're accurate. If they're meaningful labels, right? That they're labeled with the appropriate objects instead of something just very general. And if they actually accurately depict the case at hand, then they could be useful. But in that sense, they're not really a substitute for the naming that's necessary in the proof. This introduction of the items of evidence, or the arguments in the proof. You can't just say, look at the picture. So once you adopt that understanding, that the pictures are merely an aid, and they don't actually make any difference to the proof. You should be able to read a proof without looking at any picture, and it should make sense. Then, once you've done that, pictures are at best fluff. They're nice, pretty fluff, but they're not a substitute for the actual proof. And so it's good to no longer rely too much on pictures. So I'd encourage you not to do that, and again, to count off if you use pictures as parts of the proof, as a meaningful part of it. And to that end as well, avoiding overuse, at least, of symbolic notations, everys and there exist, and so on. Words should suffice for most graph theory proofs, and also we want to write incomplete sentences, not just start with notation and formulas. So it's all in the same spirit of avoiding precision. The more you can say in actual words and sentences in formal language in clearly defined terms with clearly labeled objects, the easier it is to know what is happening in the proof. And that brings me maybe to my biggest part about imprecision, and this may be the most important, is avoid the subjunctive tense. Now, for those of you who were not English majors, which probably you weren't if you're in this class, what is the subjunctive tense, if you don't remember? Well, it's a grammatical mood, most associated with uncertainty, wish, opinion, etc. It is, so if you don't know what that means, here are some examples. So it's easier to spot when you see it. So for example, if I said, if there were 2 paths such that, the if there were, it's suggesting an uncertainty, a wish, if only there were. Or you could say one can construct. It's a bit uncertainty. Can we actually do it? One may now derive a contradiction by. It should now be evident that's more of an opinion. And in the same spirit, could and must. These are all evidence of, or examples of the subjunctive tense. And I claim that we should avoid these. Why? Because there's no room for uncertainty in math. Math is certainty, it's logic, it's definition. Now, around your proofs, when just generally talking about them in everyday English, sure, maybe the use of the subjunctive is possible. For example, in a lecture. But inside a proof, in mathematical writing, I would argue that the use of the subjunctive is never appropriate. So please avoid that at all costs. And then going beyond that, similarly avoid the past and the future tenses. We always write in the present tense in math. It's always happening right now. Someone's showing you that right now. Think again of the recipe. You're cooking that chicken right now. Similarly, I would avoid ambiguity in word choice. So the problem with the subjunctive is really it's too much ambiguity and uncertainty. And we should do that when even thinking about words. So for example, if you think that must isn't actually a subjunctive, but it's an imperative, that G must be bipartite, it's ambiguous still. Because what does must mean? Does it mean that it now follows from what we've shown? Like, obviously now it must be bipartite, in which case is would actually suffice, then G is bipartite. Or is he saying this clearly must now be the case if you think about it? It's suggesting, you have to do work, but if it must be, if you think hard, in which case you should actually say why it is that case. So there's ambiguity there, and the same with can and may and those. Most of the subjunctive, again, come under this ambiguity as well. Can we? Well, are we actually constructing the thing then, if we can? Or are you just telling me we could? We can. There's ambiguity. So there are more words like this, and I don't have time to cover them, but if it's unclear what something means, that's ambiguity and it should be avoided. Continuing on, and this is in a similar spirit, is the use of course, clearly. It is clear that, obviously, those words you always love to include in proofs. And I would argue these have no place in proofs. What's the purpose of course and clearly as but an emotional crutch? Since if it were really clear, you wouldn't need to say so, right? If it's actually clear to the reader, don't insult the reader. If they can see why, then you don't need to tell them that it's clear. And if they can't see why, they're going to be mad at you for saying clearly. So, in this spirit, it's good to just avoid those. And finally, and this goes more with that, is provide a reason. If there is some reason why, and it's hard to see if something is true, and you can aid the reader, especially if it's some easy to state reason, it's good to include that. So say by theorem, tell them which theorem or lemma something follows from. Or if it's because it's triangle free, say since G is triangle free. And then this way we provide the reasons and we clear up the imprecision. We clear up on the reasoning argument why we're doing things, if possible. For the last part of this lecture, I'd also like to give you some hints or help with how to actually go about doing the writing and constructing. So we've talked about organization, a good thing to do, and imprecision, a thing to avoid. But how do you actually then go about the writing? And I'd like to argue, it kind of harkens back to English or grammar more generally, that there really are four main components of a mathematical sentence. You might want to stop and think and pause for a second. What are these components? So they're not quite like the noun or verb or adjective, those parts of grammar. I mean this a bit more generally. So here I'll go, and I'll explain each one in turn. So first, I'd argue that a sentence could begin with a leading word. What do I mean that? It usually comes in one of a few forms. A logical implication, such as a hence or thus or therefore, that's used to connect to the previous thing. It immediately now follows, right? There, hence this, thus that. It creates a nice rhythm, you don't need to do anything else. Or it might be a contrasting word, such as a but, a yet, or a however, that, we had this, but remember we had that. So we're going to get a contradiction now. Creates a contrast with the previous sentence. Or it could be an addendum word, such as moreover, in addition. Okay, we learned this thing, but now we also actually, if you think about that, the use of that theorem more, we also get this thing in addition. It's kind of creating in addition to, an addendum to what we just said. So it's not contrasting with, but it's something else. Now, a mathematical sentence doesn't have to use any of these. It could have no leading word. It could just start where it starts. And then what would we have? Well, I'd like to contend the next part is usually a reason clause. They usually come in one of two forms, a since or a by. So since G is 3 connected, you might say as G is 3 connected, but since is usually nicer. So since, G is triangle free, one of these, some properties, or it could be a by theorem, blah, by the definition of bipartite, by symmetry, by the minimality of G, and it's giving you the reason. Now you might contend that the reason clause should come at the end of sentences, and I contend actually it should come toward the beginning, immediately after leading words. Why? Because it's always good to know the reasons before you know the statements. It's always good to know the things you've already done and how they fit in before you learn new things, right? Because if you start reading the new things, the facts, then your mind starts searching for reasons. You might not even, especially if it's a long and complicated sentence, get to those reasons and start getting mad at the author, right? You want to know the reasons up front. So generally, great tip of advice, put your reason clauses second in this order. Which brings us to third. What comes after reason clause would then be a conclusive statement of fact. So, this could just be a direct statement of fact. So now G has at most 2 vertices of degree 2. Or we might do that, but preceded by what I'd say is a declaration. So we have that, we find that, it follows that. And here I explain, if you want to pause, some of the reasoning, but we have that as more immediate. We find that maybe for substitutions, and it follows that. I like to use more when a little bit more thought is needed, but if there's too much thought, maybe actually also put in some reasons. But you can develop your own sense of writing, your own different use of words. You could have your preferred leading words and how to do reason clauses and how to do these declarations of fact. Come up with your own reasoning for writing is good, but the important part is to think about it, to think through why you write the way you do. What's the best way to do it? And I'm just trying to help that along by giving you what I think are the elements of mathematical writing. And finally, there's actually a fourth one. I contend there's an end. Ending words. These don't often come up, but more to end or bracket cases, or actually ends of proofs. So they're not for every sentence, but they do occasionally show up. So for example, you might say a contradiction or contradicting theorem, blah. If we're doing proofs by contradiction, and now we've actually obtained that contradiction, or we've actually contradicted that theorem or lemma. Or for non-contradiction proofs, one of my favorites is to say as desired. When you actually obtain that object, maybe that subgraph, that vertex that you want, that exactly meets the conclusion of your theorem or lemma, say as desired. Now we have this as desired. Now case 3 holds, as desired. It just signals to the reader that, yes, we're done with this part. We've done the thing we wanted to do. We're either moving on to the next case, or we've actually finished the proof. And so those are, I would argue, the 4 main components of a mathematical sentence. And the more you get used to that rhythm, okay, how do I do this next part? Should I have a leading word? What's my reasoning clause? How should I introduce this statement of fact? Do I need an ending word? You get more used to a certain rhythm. So just to summarize overall, when writing mathematical proofs, I would argue that you do organize. Organizing, great for the reader. Break into paragraphs, break into smaller claims or lemmas as needed. Then avoid imprecision. That's really the enemy of mathematical proofs if you can't tell what they're actually trying to prove. So avoid the subjunctive, avoid ambiguous word choice, avoid informal language, etc. And finally, that word choice matters. That's really the point of those components, is you should order it as readers expect and use words that they're more comfortable with. And in math, we tend to be more comfortable with this, thus, or therefore, however, we have that, we find that, as desired, by contradiction, and so on. So think about your word choice. You don't need to keep constantly reinventing the wheel. Maybe it's somewhat preferable not to have hence, hence, hence everywhere, but a slight rotation of thus and hence and or therefore is perfectly fine. This is not, literature writing. Rather, it's actually more comfortable to mathematics to do the things that are expected, to make it more formulaic so that we can follow this technical writing, so that the reader can understand exactly what you're trying to do and exactly how your proof goes. So that concludes the writing lecture for today. In our next lecture, I'll be actually going through an example of some bad writing and how to correct it to good writing. So until then.